Hi. So now we're going to talk about the Doppler effect. You should have seen the other link that I posted to another YouTube video made by another producer, another physics teacher, about how the Doppler effect works. That's primarily for a moving source, but at the end he briefly discusses a moving observer. We are going to talk about calculating the effects of the Doppler effect. There are several main variables that we're going to consider. F is the frequency that you hear, and these are, by the way, for sound waves. There's a different equation for light waves, and we're not really going to consider that for the most part. V is the speed of the waves, so the speed of sound. And then we're going to have two sets of variables for either the source of the observer. These are O's, not zeros here. I'm sorry, I got myself confused here. And this is confusing. This is an O, so VO equals velocity of the observer. And over here, we're going to have Vs, which is the velocity of the source. But V naught sorry, man, maybe I should edit this one, but I probably won't. F naught equals the original frequency. So that's the frequency produced by the source, not taking into account motion. Okay, so we're going to do some brief calculations considering these. Now, if you look at these equations, so this, for example, is the equation with the moving observer, you can see that there's a plus or minus sign here. And that is for taking into account that the frequency might be higher or lower that you observe, depending on whether or not that the observer is moving toward or away from the source. And you should know, after watching the other video, that if the observer is moving toward the source, the frequency will be higher, but if you're moving away from the source, the frequency will be lower. So you'll choose the appropriate sign. Okay, so we'll just do this example, and again, you should pause before you see me work out this example. So violinist is playing a C sharp. Frequencies are related to the pitch of sound, so a C sharp is 554 hertz, and you rush towards them at 10 meters per second. What frequency to detect? So if you look back at the end or a couple pages earlier, you'll remember that the speed of sound in air is 443 meters per second. So we'll put that in here, and we'll see F is equal to 1 plus or minus. So we're moving toward the violinist, right? So we'll use plus. The frequency should increase. V naught over V. Or sorry, it's not V naught, it's VO, right? And this is F naught. Right? So we'll have F is equal to 1 plus V of the observer is 10 meters per second. Speed of the waves, 343 meters per second. And the original frequency is 554 hertz. So we'll put that into the calculator. 1 plus 10 over 343. And multiply that by 554 hertz, and we get 570 hertz. Part 2 of the question is, what frequency would we detect if we run away instead? And of course, it's a very similar calculation. We're just going to use the minus sign. So F is equal to 1 minus 10 meters per second over 343 meters per second. 554 hertz is equal to, oops, don't know what buttons I'm pressing. Looking at the screen instead of my calculator. Okay, times 554. So we get 538 with 3 sig figs. Okay. Now, if we look on the next page, we see that the equation for a moving source is slightly different. So first thing, you'll notice that the plus and minus are switched, right? You also see that the velocities are in the denominator instead of the numerator, right? So we're not going to derive this equation. We can just use this equation. You'll just have to remember that this is the equation for the moving source, and you should remember that because the S is down here with the V. The reason that the negative is on top, because if you're moving it toward if the source is moving toward the observer, right, we should expect a higher frequency, right? Well, if this is in the denominator, the negative sign will give us a higher frequency because we are subtracting, making a smaller denominator, therefore a higher frequency. Okay, so let's come up with an example. Let's estimate the example in the video. Now, I don't remember if he told us what numbers he used, so we will make up numbers. We'll say that F naught was, we'll use 440 hertz because that is the middle A value. I forget which one is that, A3 or something like that. And we'll say that the speed of the source, he was in a car, but it was kind of slow moving. So we'll say maybe it was about, we'll say it's 15 meters per second. Let's say 15.0 meters per second. Okay, and we know, of course, that speed of sound in air is still 343 meters per second. So we want to estimate the frequency that we'd observe as he is approaching and as he is leaving. Okay, so as the car is approaching, we're going to have 1 minus Vs over V times F naught. So this is the approach. 1 over 1 minus, we have 15.0 meters per second over 343 meters per second times 440 hertz. 1 over 1 minus 15 over 343 times 440, and I get 460 hertz. And then when he withdraws, we get the plus sign on the bottom. So 1 over 1 minus 15.0 meters per second over 343 meters per second times 440 hertz. And we plug all that in. And I get 422 hertz. Okay. Now, in principle, you can combine these so that you have a moving observer and source. And you can also find what happens if the relative speed between the observer and the source is very small. This is what we frequently do with the Doppler effect of light, because usually things are not moving very quickly compared to the speed of light. But I am not going to ask you questions about those. We're going to stick to sound waves in this class.